Okay, so we're on page 58 in your notes, and we're about to talk about naming trig graphs. And what I'm going to do is, before we actually begin the naming process, I'm going to give you a set of directions. I believe at the bottom half of page 59 there's a big blank space, and you can use that space to write what I am going to write above the notes on page 58. So I'm going to just kind of add in some notes up here at the top, and the notes that I'm going to add in are basically the step-by-step process that I encourage but not require. There is only one step that I'm going to require, and the step-by-step process goes something like this. The very first thing that I'm going to want you to do when you are trying to name a graph is to find the horizontal middle of the graph. I'm going to call that the midline. And that midline is always going to be a y equals equation. And you're going to find it by just essentially extrapolating the middle, or the distance between the highest and the lowest points. Now, the biggest issue with finding the middle is largely that, hang on, I'm having technical difficulties again. The biggest difference between finding a middle and is largely that if I don't show you the whole graph, it's kind of hard to find the middle, but you can usually extrapolate pretty easily. So if I tell you I'm going to ask you to find the middle of that graph, what's the issue going on there? I said find the distance between the highest and the lowest point. There's no lowest. I'm not looking at a whole graph. So you do have to use a little bit of common sense when I say that. You've got to be looking at one complete cycle of a graph. If it's a cosine graph, you should see a full smile. If it's a sine graph, you should see the full S. So whatever the distance was from here up to here, it would be the same distance down to the bottom. And you need to know that when you're trying to extrapolate that middle distance. So whatever this graph was, this would be the midline, whatever that number is right there, and you can figure that out by basically just determining, even if you don't see it, determining the average or the middle of the distance between the highest and the lowest. We okay so far? Okay, so now that I've got that determined, the next thing I'm going to ask you to do is to name that midline with a number, and that number is really quite legitimately just the height of the midline. So I'm going to go down to this first graph, and I'm going to begin my process by, I'm going to draw in the midline, and I can see very clearly on this one, although I can't draw it right where it's supposed to be, that that midline is right there, exactly halfway between the highest point, which would have occurred right here, and the lowest point, which would have occurred right there. That makes my midline for this one, y equals 3. So basically where I'm getting that from. And I'm going to start writing the name of this equation, but when I write y equals 3, I'm going to write y equals big ol' honk in space, and then plus 3 over here. So I am writing y equals 3, but I'm leaving space for the rest of the name of the graph. You'll remember that midline, or that vertical shift, was basically just a number that got added or subtracted at the end of the trig function, and that's effectively what I just did. So basically where that comes from. Now the reason that's got to be the first thing that you do is because the second step in the process of naming a graph is to determine whether the graph is a sine or a cosine graph. And the decision about whether this is a sine or a cosine graph comes from finding the intersection on the y-axis, which is to say, if the graph intersects on the y-axis at the origin, and I'm saying origin with a little bit of emphasis there because the origin that I'm speaking about is not necessarily the real one, but the one that would have been the origin if I were graphing this. So the fake origin, or the intersection of the midline and the y-axis. That intersection, if it hits the graph, makes the graph a sine curve, and if it misses the graph, makes the graph a cosine curve. So this one hits the graph, that makes it a sine curve, which if you're paying attention to the directions I already told you, starting kind of easy here. So this is a sine curve because there is an intersection with the y-axis and the midline. So basically where I'm getting that from. Okay, so I'm going to go ahead and write sine in here. You'll notice I'm not writing it just to the right of the equal sign. I'm leaving a little space in front of the word sine. What am I leaving space for in front of the word sine? The amplitude. And I'm leaving a little space before the +3. What am I leaving a little space there for that? For the angle and the frequency. I'm going to need to put in a theta. I can put in theta now if I want, but I got to leave a little space between the word sine and the word theta because I don't know how many cycles of a sine graph I'm seeing here. Still good? Okay. The next thing I'm going to do after I've decided that this is a sine or a cosine graph is a two-step process which is going to help me find the amplitude. And the amplitude is basically just the distance from the highest point down to the midline. Now that I said this was a two-step process because that distance is always going to be positive. If I go from the highest point down to the middle, I know I'm going to get a positive number, but that doesn't mean it's a positive graph. So the second part of this, I'm going to call it step 3A, is determine whether the graph should be named positive or negative by looking at whether the graph is upside down or right side up. So because this is directions for you, I'm going to put upside down / right side up question mark. And obviously an upside down graph would be a negative amplitude, and a right side up graph would be a positive amplitude. Is that basically where I'm getting that from? So for this graph that I'm looking at in the first example here, the amplitude that I'm going to go with is going to be a +2. And I do want to see that positive there. Having the positive in front of the amplitude shows the reader, the grader, the teacher, whoever it is that's grading your test or regents exam. Remember, your regents exam won't be graded by me. So it's showing the person who's grading your regents exam, which I can promise you is not me, that you've thought about it. That it's not just a 50-50 luck of the draw that you happened to get it right, but that you actually gave thought to the fact that this was a right side up graph. So I do want to see that positive there. It's a moderately important positive. Is that clear? Okay, last but not least, and probably the hardest part of the process, is coming up with the frequency, because the frequency is largely dependent on where the graph was supposed to end. Now these graphs, you'll notice, are not labeled with a width, so I'm going to start by making them kind of simple, but first I'm going to give you the process. And the process that we're going to use is going to be to set up a proportion. And this proportion is, again, to help us find B, or the frequency. So I'm looking to find B, and I'm always going to do it by kind of exploiting the period and where one graph is supposed to end. So I'm going to set up a proportion that effectively will read 2 pi over B on the left. Essentially, this is the formula for period. And the formula for period is a normal width over a normal number of cycles. And I'm going to set that equal to my chosen width, and I'll show you what I mean shortly by my chosen width, divided by my chosen number of cycles. And the number of cycles that you see is typically going to be a fraction out of 4. And that fraction out of 4 comes very much from just the fact that every trig graph has 4 unique parts to it. And they are part 1, part 2, part 3, and part 4. That's a sine graph. A cosine graph also has 4 unique parts. They're just in different places. But part 1, part 2, part 3, and part 4 are very much the same parts. And I kind of tried to color code them here so you can see they both have a part that starts at the x-axis and goes up. They both have a part that starts at its high point and goes back down to the x-axis. They both have a part that starts at the x-axis and goes down, and they both have a part that starts at its lowest point and goes back up to the x-axis. So those 4 parts are kind of equivalent. They just happen in different places, but they both have 4 unique parts, and those 4 unique parts are those 4. Still good? Okay, so now I've got those 4 parts, and I'm going to show you how to box off or capture a section of graph by going to this example that, if I say please, that was on our previous page, and I'm going to put a box around a section of the graph. Now, it really doesn't matter what choice you make for the section of the graph. What matters is that you are consistent. So I'm going to start by making this box right here, or this distance out here. I'm going to label it up at the top so I've got a little bit of space. I'm going to let that be 3 pi. And I'm trying to make this a little bit hard, but not terrible. So I am going to start my box, my choice, by picking a rectangle, and I am going to go with this right here. I'm going to box off that particular section. Now I'm choosing not to do the whole graph just to show you that it really does work. So if 8 boxes was 3 pi, what distance or what width would I have hit halfway across? 1.5 pi. Okay, so I'm going to write the proportion. 2 pi is to be as, what fraction of graph is in that box? Out of an entire sine graph, what fraction have I boxed off? Half. I box off half, or 2 of the 4 sections that I need to see. So I can say now, I see, sorry, that goes on the bottom. I see 2 sections in a space of 1.5 pi. Now once again, the proportion is always going to be 2 pi over b on the left, my width, which is 1.5 pi, over my sections of graph, which is half. So the proportion I've got set up now is 2 pi is to b as 1.5 pi is to 1/2. After that, you're just going to cross multiply and find b. 1/2 times 2 pi is 1 pi. And b times 1.5 pi is 1.5 b pi. Now the pi's cancel on both sides, and you end up with 1 equals 1.5 b. And if you want to know what b is, you'll divide both sides by 1.5. Now I'm not a big fan of these complex fractions or fractions with decimals in them. So I'm going to ask you to simplify that by thinking of this as 1 over 3 over 2. And I want a fraction that means the same thing, but is no longer complex. Anybody know what that's going to be? Brendan? 2/3 is correct. So 2/3 is the number that goes right here, which is to say, if I were to go only to 2 pi, what part of the graph would I have seen? And logically that makes sense. If it took me all the way out to 3 pi to get one full graph, then at 2 pi I would have been 2/3 of the way there. Now I know a lot of you could have figured that out without this process, but what if I had made the x value right here a 12? Then it's a little bit less easy to figure out, because over here I gave that x value a pi number, which is what it's supposed to have. Over here I'm giving it a real number, which is not what it's supposed to have. So now I'm going to need that process, and that's why I show it to you. Because in real life, things are not counted in pies. In real life, sunrise and sunset are not counted in radians. They're counted in 1 whole hour increments. In real life, the tide is not counted in pies. It's counted in 1 whole hour increments. So I need to be able to come up with an equation for tides or for sunrise and sunset that will still accurately graph the sunrise and sunset, but doesn't require me to count in a clock that counts by pies, because you're not going to find one of these everywhere. So in this case, start the same way. First thing I do is I find my